Hello everyone, I'm Niket Agarwal, a software engineer at Meta, and today with my colleagues Johannes and Dan, we're going to talk about transparent memory offloading or TMO, a technique we've used in Meta's data centers for over a year to yield memory efficiency for our fleet. I'm a system architect and I've been working in the memory area for quite a while. First, let me talk about an accidental coincidence between COVID and TMO. You might remember in the early part of 2020, when COVID was hitting, the world was shutting down, the cases were rising, and back then, the traffic to our fleet in Facebook and Instagram was shooting up. We were seeing a huge demand for our workloads and our apps inside the fleet. However, the world was shut down, so it was not like we could just buy in a bunch of servers, ship them to our data centers, and meet the traffic demand that our workloads were facing. We had to make more efficient use of the existing hardware in our fleet. We had a huge capacity crunch back in the time. When COVID hit, this also coincided with an ongoing program we had been working for quite a while. As some of you might know, memory cost is an ongoing industry-wide problem. This chart here on the x-axis is showing generation over generation the cost of memory in the fleet. The y-axis is the percentage of memory cost as compared to the overall infrastructure spend that we do. Today, memory cost is about 33% or one-third of our infrastructure spend. It's pretty high. So we've been working on ideas to get memory efficiency to make sure the memory cost of our fleet was not that high. So what technique did we use? As some of you might know, this is a traditional memory storage hierarchy pyramid. At the bottommost are HDDs or hard drives, which are pretty cheap but also pretty high latency for accesses. And at the topmost are caches and DRAM, which are very close to CPUs. So they are very low latency, high performance, but they're also very costly. So what we were trying to do is figure out how to put memory that typically requires DRAM into slower memory tiers like NVMe or SSD. So let me give you a brief introduction on what transparent memory offloading is. So this picture is showing RAM, where most of the memory used by applications sit. There's a bunch of memory that we call infrequently used pages. These are pages that are not touched by the application very often. So we looked at two techniques. First is if we could take some of the infrequently used pages, compress them, and put them into a pool of memory that's still in DRAM, we could use less memory for those same pages that were in DRAM. This would yield more memory out of the existing memory in the fleet. Secondly, we could swap those cold pages and put them on SSD, which is cheaper than DRAM. This way, we found a cheaper media to put the existing pages that applications need. Both of these techniques complement each other, and we were building a TMO technique to transparently do this across the fleet. So early exploration, this is early 2020, was giving us very promising results. This chart is showing on the x-axis a baseline tier where we were not doing any TMO, and on the right-hand side, it's showing TMO enabled for the same exact workload. The y-axis is showing the resident memory or the memory used by the application. It was about 40 gigabyte when we were not using TMO, and as soon as we enabled memory offloading, the used memory on DRAM went down to 20 gigabyte. So we were seeing 50% memory reduction for this workload when TMO was enabled. This was very promising. However, we were very far away from productizing TMO across the fleet on a number of applications. With that background, let me hand it over to my colleague Johannes, who's going to talk about how we scale memory offloading from early benchmark results to large-scale deployment in the fleet.
Thank you, Niket. My name is Johannes Weiner. I'm an engineer on the Meta kernel team. Today I'm dialing in from upstate New York, where you might be able to see the remnants of the last snowstorm still outside. And today I'm going to talk about the sort of key takeaways of the first phase of our transparent memory offloading efforts. So the first experiment that we conducted was fairly straightforward. Because of the capacity crunch, we had several of our web servers running on machines that were just a little under-spec for what they needed for the workload. Specifically, there was not enough room to hold all the file system cache. And because of that, we saw a lot of disk reads, and those would eat into the total performance of those systems. So the idea was, hey, what if we just added some swap space to those setups, and maybe the kernel is smart enough to balance the pressure out a little bit, offload some of the lesser used heap memory, and make room for the file cache, and have everything perform a little better. Unfortunately, when we added swap, just nothing changed, nothing happened. I'm going to explain why. So it turns out that Linux is really reluctant to actually engage swap. And the reason is because the swap code is really written with mechanical hard drives in mind. And those are pretty bad in terms of the handling the random I/O patterns that are coming out of swapping and paging in general. And so the policy is really for Linux, just unless you're about to kill the workload, just try not to swap at all. So we avoid jankiness and being unresponsive and all of that. But of course, most modern computers have SSDs and flash storage, including our web servers. So the first thing we had to do was we had to teach Linux about actually taking advantage of that and making use of that additional capacity. So here's the new swap algorithm that we came up with. First, we're tracking all of the swap ins and all of the cache misses that are going on in the system. And then on the top of that, we have a feedback loop that just says, for every cache page that we're reading from the disk over and over, try to swap out one heap page. And so if we're unlucky and that heap page swaps right back in, this is not a really big deal because while it happened, this is just one cache miss that didn't occur at the same time. We're just going to push back on the cache, right? So no harm, no foul. But if we are lucky and that page stays swapped out, that's cache space that we can now use, right? So in practice, what this means is that we're starting to engage swap a lot earlier in many scenarios, but we're only ever trading paging that's happening over here for paging that's happening over here. So we're not adding to the IO load. We're simply being more intentional about where to apply IO and where the paging happens. And once we had this in place, our web servers started to look a lot healthier. As you can see, that when we added swap, the heap shrunk, it got offloaded to the swap space, and the files could just expand a little bit, and the whole system relaxed and performed better than it did before. So this was a very encouraging result because it means we had the first tool in the crisis to help some of the most distressed services out and have them run at a better performance. But it also raised a bigger question, which is, if we can improve things without actually adding more memory, can we also take away memory from workloads that are healthy right now without hurting them? Because that's where the real memory savings would be. And with that, I'm going to hand over to Dan, who's going to talk about how we approach this.
Thanks, Johannes. I'm going to talk about measuring memory and how we've sort of tackled this problem in the context of TMO. One of the things we like to say when we talk about memory is that it's really not a scalar, but it's a probability density function. So I can actually chart my memory use as a function of how often I access it. In the chart here, we've sort of shown that on the right, we have very infrequently accessed memory. And it might be a lot of it, but all that memory we should be able to offload. And we can just load it back in from the backing store because it's infrequently accessed. This shouldn't impact the application all that much. On the other end of the spectrum, on the left, we have the hot memory, and it definitely needs to be kept resident because it's frequently accessed and the cost of loading it in from a backing store will be too much. And then we have this area in the middle, which we call the warm memory. And the problem there is that how much of that you can offload is really dependent on the characteristics of your backing store. So if you have, say, a slow spinning disk or slow SSD, then you probably can't offload much of that. It's far too frequently accessed for you to pay the cost. But if you have, say, a compressed memory or some very fast SSD as your backing store, then you could load that stuff in pretty frequently and still not see impact on the application. So when we deployed TMO and we had customers using swap, we found there was actually this issue where they would ask us, how much memory does my application actually need? They would need to know so that they could provision how much memory that their server actually consumes. And what we found in doing this is that the only way for us to properly tell them is to just continuously offload the memory. Rather than waiting until the machine was out of memory until it was a dire situation, we actually wanted to proactively offload as much memory as we could, and everything left over, that's the memory they truly need. And this should adjust for the speed of the backing store that they have. So to do this, we came up with two technologies. The first is PSI, and PSI is a kernel component we developed that tells us exactly how much the application is suffering because it lacks memory. The way we do this is we track stuff like page faults and see how long are we spending on a page fault, and we we track that as a stall. We say, like, okay, this 10 milliseconds or so, the program didn't run because it lacked memory. And then we can kind of export this as a percentage of the compute potential that was wasted. So 10 milliseconds over however many seconds of compute potential we had in some unit of time, and say, okay, 2% of the time this application suffered because it lacked memory. And the idea with PSI, therefore, is it tells us, one, how much time was wasted because we lacked memory, but also it scales with the storage speed, right? So if our page faults are longer, then our stalls are longer, and therefore PSI should go up. The other component we implemented was Senpai. And Senpai is a user space agent that basically drives just a little bit of reclaim until we see PSI, the pressure threshold, go up a little bit. And as soon as we see the application is just starting to suffer from a little bit of lack of memory, that's when we're going to stop. We're going to stop reclaiming memory. And everything left over is what the application needs. So kind of our diagram in action here is there's this pressure threshold that we want to maintain for sensitive application, potentially application that needs a lot of latency preservation. We're going to keep a pretty low threshold. Some kind of batch applications, we may set this a little higher. But Senpai basically says, as long as the pressure is above this threshold, we do no reclaim. As soon as it drops below, we'll do a little bit of reclaim. And as it keeps dropping, we'll do more and more as long as we can preserve this pressure at the threshold. And in doing so, kind of see that pressure oscillates along this threshold. And in doing so, what we can say is all the leftover memory, that's what the application actually needs to perform well. Everything else we can offload. And therefore, users can actually measure how much is resident. That's the amount of memory they need in their service. I'm going to hand off to Johannes next, who's going to talk about compressed memory.
All right. So now that we have our rudimentary offloading tools in place, we also started experimenting with a different offloading backend, which is memory compression. So this component is called ZSwap, and it's the same principle as swap, where we're taking pages that are kind of cold and less used out of the heap, and we're offloading them. But instead of writing them to disk, we're just compressing them in space. What this means is that on a page-per-page basis, that is still consuming more memory than if we had written it just out to disk. But because it's so much easier and quicker to bring back, all we have to do is decompress it and not have to go to disk and read it back, we can offload a larger share of the workload this way, which is especially interesting if the workload has a larger warm set that might be a little too hot to move it out to disk without hurting the workload. So if we have workloads like that with a large warm set that also compresses well, which is a bit of a caveat, then we can save more memory this way. And for some workloads, this is true. For others, it might not be. So depending on what we have, this is a decision we have to make in our deployments. But as an example, when we tried it out on our web server load, we saved some memory with regular swap, but we saved even more memory with ZSwap. And one cool thing I would like to point out is that when we switched from swap to ZSwap, because our offloading stack is targeting a specific paging overhead that the workload is experiencing, we had to do no tuning other than switching to a faster offloading backend. And our entire stack would automatically adapt and offload more memory this way. And that's something that would come in very handy later on, just because we have a wide variety of different flash drives in our fleet, and some are slower and some are faster. So at this point, we have a very promising approach to offloading, and we have some very encouraging first results too. But obviously, there's still work to do before we can have something that works in a lab to something that works in production at scale. Dan is going to talk a little bit about how we get from A to B.
Thanks, Johannes. So I'm going to talk about our path to production. And getting back to the start of the talk, we hit this period of COVID where we were, really desperate to figure out ways to save memory. And as we sort of mentioned, what we had with TMO wasn't complete. We had a lot of unanswered questions and really no time for a perfect solution. So one of the first problems we hit was, as Johannes mentioned, compressed memory works for some applications, but not well for others. And we couldn't figure out exactly the right way to dynamically configure between the two. Similarly, Senpai had a lot of different configuration knobs. There's the periodicity with which it reclaims memory, but there's also the pressure thresholds that you can configure, which may work better for some applications than for others. But instead of waiting for the perfect solution, we just tried to ship what we had and figure out ways to get immediate solutions. So the first thing we did was we just worked with some of the biggest services that we had and allowed them to choose, does Z-swap work better or does disk swap work better? And with experimentation, we would figure out the best solution. Similarly with Senpai settings, we played with a lot of different configurations, but we figured, hey, let's just try to save something for everyone and really err on the conservative side so that there would be no performance impact, but we could still save quite a bit of memory. This diagram on the right shows the behavior on one of our web servers where, with TMO disabled, we've got the memory pretty flat as it's running. These dips are periodically the server restarting. And then the middle section we show we've enabled a conservative config, and you can see this gap as memory grows. We're able to save more and more with TMO. Now on the third side we showed a much more aggressive config, and you can see rather than this gradual decline of memory consumption, we actually get this much sharper decline and huge amounts of savings. But we found when doing this that it was impacting the performance of the web server a little bit, and we weren't quite happy with the amount of performance we were giving up for the memory savings. And even the modest savings we were able to get in the middle was enough that no longer were the web servers memory bound, and we were able to just compute more with our existing servers. So this was an important point for us, that we were able to just save a little bit. It wasn't the best for all the applications, but we worked pretty closely with some of our biggest applications like web, Instagram, some of our ad services to make sure that they all got quite a bit of savings and unblocked their progress with the kind of shortage of servers we were facing. The other thing we hit that was quite interesting while we were going to production was that disk write endurance became a substantial concern. We run a lot of SSDs that don't have the greatest write endurance, and we were finding that with all the swap out we were doing with TMO, especially with disk swap, that it was quite costly in terms of the write endurance. We were hitting cases here we see P90, 5-6 megabytes per second of write, which over the lifetime of an SSD, if we're constantly pushing that, could wear them out sooner than we project. So this is a case where we had to scramble pretty quickly and add some new logic to Senpai to not just look at pressure, but also look at swap out rates and modulate it. And here we show that with modulation turned on, Senpai is able to still do reclaim of file cache, but avoid reclaiming swap. So we avoid all the writes on the disk, and we're able to keep some target write rate, in this case 1 megabyte per second. And doing this, we were quite successful. We were able to get this shipped out to a number of our largest applications and get them running successfully, saving quite a bit of memory throughout the fleet. I'm going to hand off to Niket next, who's going to talk about our overall fleet results and give some more color into how that worked.
Thanks, Dan. With that background, let me walk you through some overall fleet results of how TMO has been performing in our data centers. This chart shows a summary across major workloads in our fleet, how TMO has yielded a lot of memory savings. The x-axis shows the major workload types in our fleet, and the y-axis is showing memory savings percentage, or how much per server memory are we yielding from TMO enabled on these services. As you can see, across both compressed memory offload as well as SSD offload, we get anywhere from 5 to 20% memory savings. This is a lot of memory that we've yielded back to our services, and they have resulted in a lot of power as well as capacity wins over the last 1+ year. Our journey is not yet done. There are a lot of enhancements we are doing to the TMO stack, as well as working on future work on extending TMO. Recall back to the original storage memory hierarchy pyramid that I showed. If you remember, the topmost memory storage technology was cache and DRAM, which tends to be pretty pricey but also very fast, whereas hard drives tend to be very cheap but also very slow. There's advent of new memory technologies in the industry called CXL, or Compute Express Link Memory. This fills in the gap very nicely between DRAM and NVMe SSD, and is very attractive to the entire industry as a memory device that a lot of people are working on. Here at Meta, we are also investing a lot of energy in building hardware as well as software techniques to extend TMO for this new memory technology. And please look out for early results from our work coming very soon to conferences near you. Thank you for listening to our talk.